In this video we're going to be looking at op-amps as comparators, and comparator is nothing more than a circuit which is set up to compare two currents or two voltages or whatever the particular input happens to be. Right, in this case we're going to be looking at voltage. So our op-amp in the middle here, plus and minus, and we're going to have our output voltage here, but we're going to have a slightly more complicated connection around the input to this particular op-amp. Now we're going to have two supply rails. In this case it's going to be a single supply, so 0 volts, this is ground. It doesn't have to be. It could be dual supply rails. Well, what you'll note in this particular circuit is that, and let's say this is B plus, that we have no negative feedback. So we are not designing an amplifier. Alright, not making an amplifier. We're using an operational amplifier, an op-amp, as a comparator. So in this case, we actually want the output to saturate, so that the output can only be at one of two particular voltages, roughly, either at the positive supply rail or the negative, or in this case grounded supply rail. So let's see how this works. In our circuit I've got a sensor and I've got a couple of resistors, R1 and R2, where R1 is equal to R2. So this point here is 0.5 times the input voltage. Now, as we know, it's got a very large gain in this particular circuit. We're not too concerned that the gain's going to be non-linear and it's going to be really high or any of that, right? We're actually only interested in comparing a binary decision. Is the voltage at the non-inverting terminal greater than the voltage at the inverting terminal? That's all we want to know. And if it is, then then make the output high, and if it isn't, make the output low. So let's see how this would operate. So with respect to time and voltage, here is Vn and Vp. Here's Vn, which is equal to 0.5 V plus, so half the voltage supply rail. There's 0 volts. And I'm going to draw Vp in blue and V out in green. So I'm going to go, let's say our sensor voltage increases linearly with time up to some value, and then decreases linearly with time down to some value. So it looks like a sawtooth or a triangle wave. Right, so we have increasing Vp and then decreasing at some point. Whatever it happens to look like, that's fine. When we begin this simulation, or let's say the operation of the circuit, at this point here, output voltage, as we remember, V out is equal to the open loop gain times the difference between the input voltages. This guy is really big, let's say 10 to the 5. Okay, maybe it varies from 10 to the 4 to 10 to the 5. Doesn't really matter. All we know is that if there is any small difference between Vp and Vn, then it will be greatly amplified. Okay, so any small difference between those two is going to be greatly amplified, whether it be positive or negative. If it's 0, then we should get, remember our output voltage should be 0 because the common mode gain should be equal to 0. So let's have a look what happens. To begin with, Vp is 0, so let's come down. This point here I'm going to call point A, This point here I'm going to call point B. This point here, C and D. In fact, just change those names again, C, D, and E. Right, so we have 5 points associated of interest within this particular operation. Now, at point A, the voltage at VP is 0, and the voltage at Vn is half VCC. So at A, Vout is equal to the open loop gain times 0 minus V plus over 2. So we get a negative voltage times AOL. Now remember that Vout here is limited by VCC and VEE, these two values here. So it can't exceed those two values, which in this case is 0 and let's say V plus. So any negative value times a really large number is a really large negative value. So the largest negative value that we can supply from the circuit is in fact 0. Whether you want to call that positive or negative is up to you. So at this point the output voltage is 0. And in fact for the entire time that Vp, this blue line, is less than Vn, alright, we will end up with a negative number. So even at the point where we get Vp minus Vn and we get V plus over 2 minus V plus over 2, we get 0. So even when Vp equals Vn, this equation goes to 0, so we stay on the 0 volts point. However, as soon as we exceed, okay, so we get a little bit past, so Vp, let's say, is equal to Vn plus very small number, okay, it doesn't have to be 1e minus 6, for example, volt. As soon as it exceeds it, then this term here becomes a positive voltage. Alright, so we would get Vp minus Vn equals, for example, 1e minus 6 times a really large number. It's going to give us a very large output voltage. In fact, let's make it so it would be a very large number, so 1e minus 3 volts. Okay, therefore at this point here our output goes high. Alright, very small number times a very large number here gives us a very large output voltage, limited by always the power supply rails. So we put here V plus, we will continue on at that voltage, and in fact while Vp is greater than Vn we will stay high. However, at point C remains the same, okay, very large, so we'd have a large positive number here multiplied by a large gain, gives us still a very large output voltage. Once they're equal to each other again, we get the same condition as B. So really, effectively the same thing happens there and the same thing happens there. So we would continue on at 0 volts here. So you'll note that the circuit has this comparator function. When the voltage output from the sensor exceeds the reference voltage, okay, this temperature could be, for example, dependent on temperature. So when the temperature exceeds a certain value, which you could set by designing R1 and R2 to be according to a particular temperature, then the output of this could go high, indicating, for example, your freezer stopped working, or temperature outside is no longer safe to work in, or whatever the situation may be. As soon as the temperature falls, the voltage output from the sensor falls, right, the difference here goes negative, and therefore the output goes back down to 0 volts. The buzzer goes off, the light goes off, or whatever the circuit may be. You can get the same operation but reversed, okay, so it's high and then goes low, if you just swap the inputs. Alright, so if your sense input goes to the inverting and your reference voltage goes to the non-inverting, with exactly the same graph, you would have high at this point then low, then high again. Alright, so you could flip the operation depending on whether you want a high or low alarm. Okay, and all we've done is use that same expression that we saw for the differential amplifier, and we're just looking at Vp minus Vn. If that voltage is positive, then a large number, AOL times the positive voltage, will give us a very large positive output voltage, so we're going to hit VCC. If Vp minus Vn is negative, times a very large number will give us a very large negative number, which will take us down to the limit of VEE.